Okay, let's go ahead and continue. What we've done so far is we've completed the first three steps that we proposed in this process of studying solutions to initial value problems, right? Now we're finally kind of ready to go and return to our initial problem that we had sketched up. Okay, so what we have is we finished this guy. We're now at step 4, right? Which is solutions to the state space initial value problem, right? So we're finally ready to return to the full generality case. Now the amazing thing is that the solutions to state space initial value problems are entirely characterized by the state transition matrix. Okay? So knowledge of the state transition matrix will enable you to solve a state space initial value problem, as long as the system is linear time varying, for any input as long as it's piecewise continuous. Okay? So this really gives us complete knowledge of what our solution is going to do. Okay, so with that said, let's go ahead and state this theorem. So what we have is theorem, existence, and uniqueness of solutions to the state space initial value problem. Okay? So what I'm going to say is, let's just take our standard piecewise continuous data, right? So let A be in PC of R, Rn by n. B belong to PC of R, Rn by m. And U, my input, belong to PC of R, Rm. All right? And what we have is that the unique solution to the initial value problem, right? The state space initial value problem, x dot of t equals a of t x of t plus b of t u of t, x at time t naught equals x naught, is given by the formula. Is given by the map x going from R into Rn, which is defined x at time t equals phi of t, comma t naught, times x naught, plus the integral from t naught to t, phi of t, comma tau, b of tau, u of tau, d tau. Okay? And this has phi as the state transition matrix with respect to A. All right? So the only additional thing we need to compute the unique solution to this initial value problem is the state transition matrix phi. All right? So phi is characterizing pretty much the entire structure of this solution. Great. Okay, so let me just go ahead and give a really quick sketch of this proof. All right? So the details don't involve anything fancy. It's just a couple of basic computations. All right? So the easiest way to kind of prove that this solution holds is to go with this differentiation route. So first what you would do is you would verify the derivative property. Okay? So you would take the derivative of x at a point which the data is continuous, and you would do this via the Leibniz rule for differentiation under the integral sign. Okay, so if you haven't heard of this before, this is contained in the notes, and it just gives you a nice formula for taking the derivative with respect to t when the functions inside your integral depend on t. Okay? So the derivative property will just directly pop out of this, Leibniz rule for differentiation. Okay, property 2. So in order to verify the initial condition property holds, what do? Well, you have x at time t naught is equal to phi of t naught x naught plus an integral from t naught to t naught, which is just immediately 0, right? Now phi of t naught is just equal to the identity times x naught, which equals to x naught, okay? So the initial condition property is satisfied. Then finally, for uniqueness, you just do the same thing that we've been doing for uniqueness so far, okay? So you just take two solutions, subtract, take the norm of the difference, and apply Gronwall. All right? And what this will show you is that those two solutions need to be equal to each other for all time. All right? So those are the 3 steps you need to do. They're all fairly straightforward computations, okay? I would recommend trying them on your own. If you want to check your solutions, just check the corresponding section in the notes. All right, so that's a proof. All right, so this is what we've kind of been leading up to all lecture, right? So let's just quickly go over what the consequences of this result are. So the consequences of the theorem. So our original motivation for studying initial value problems was that we wanted to have a well-defined state transition map from our state space system representation, right? So what this theorem tells us is that we have a unique solution to this initial value problem that's given by the representation, right? So this tells us the state transition map of the linear system representation must be well-defined. Okay, so as long as we pass in piecewise continuous data, the state transition map will have, a well-defined value. Okay, all right. So further, what this theorem tells us is we can kind of compute the state transition map via phi of t1, t naught, x naught, u equals phi of t1, t naught, x naught, plus the integral from t naught to t1, phi of t1 tau, b of tau, u of tau, d tau, right? So this gives us actually an exact formula with which we can compute the state transition map for a linear system. Okay? Now that we have the state transition map, what we could do is we can actually verify that a linear time varying system representation yields a formal linear dynamical system. Okay? So to do this, what you would do is compute the IO map rho. And remember, we compute the IO map by substituting the state transition map into the readout map of the system, okay? Which in this case is just the output equation. So what you would get is that rho at t1, t naught, x naught, u is equal to c at time t1, phi of t1, comma t naught, x naught, plus c at time t1, integral from t naught to t1, phi of t1 tau, b of tau, u of tau d tau, plus d at time t1, u at time t1. Okay? So all I've done here to compute rho is I've substituted my state transition map into the output equation of the linear system representation. All right? So there's a couple of interesting facts about this. First, what we see is that we actually have 2 separate components, right? So this component in blue doesn't involve any input terms whatsoever, right? It just relies on the initial condition. So this is called the zero input response of the system. And then the second term over here doesn't rely at all on the initial condition, right? It only relies on the input. So this is called the zero state response. All right. So notice this is also sometimes referred to as the free response, and this as the forced response. All right. So that's a nice consequence of this particular structure of solution. All right. We could split our solutions into 2 different components. Now, what other consequences do we have? Well, notably, if we take a look at the structure of the solution, what we see is that rho is indeed linear in the product of the initial condition and the input signal, right? So remember, this was really that big property that we were trying to prove in order to show that linear time varying system representations actually lead to formal linear systems. Okay, so this big linearity property is satisfied, and what that tells us is that finally, after a little bit more work, just verifying some formal composition axioms and all these different things, linear time varying state space representations yield formal linear systems. All right, where by formal linear system, I mean a linear I/O causal dynamical system in the sense in which we defined in lecture 1. Okay, so that pretty much completes this process over here, right? We verified that these linear time varying system representations do actually go ahead and give us formal linear dynamical systems. All right. What's more, we kind of learned a little bit about the structure of these dynamical systems. Okay, great. So I promised we would talk a little bit about the discrete time case, right? So discrete time case. Now, thankfully, the discrete time case is significantly easier than the continuous time case, right? So let me give just really a quick outline of the analogous theory, and we'll get a feel for why it's so much easier. Okay, so let's just go ahead and just kind of sketch out a very similar process to what we did above, right? So first what we did is we studied solutions to the state equation of the representation. Okay? Now, in the discrete time case, the state equation, instead of being a differential equation, it's a recurrence relation, right? So what we have is x at time step k plus 1 equals a at k times x at k plus b at k times u of k. Now, a really nice feature of this is that solutions are automatically defined and they're automatically unique, right? So solutions exist and are unique. And the reason for this, right, is that we're always just directly specifying what the next step in our process is, all right? So if I say go ahead and I give you an initial value problem, I say I want this to be satisfied and I want x at time k naught to equal x naught, I'll immediately get a unique solution x, which goes from z k greater than or equal to k naught into Rn, okay? And the reason for this is we just keep applying this recurrence at every step along the way. For all times greater than or equal to k naught, we'll be able to define our solution, okay? So that kind of gives us existence and uniqueness of solutions to these recurrence relations pretty much right off the bat, right? What else do we have? Well, we have that solutions actually, maybe somewhat surprisingly, have a similar structure to the continuous time case. All right, so you could go ahead and you could define your state transition map, and it turns out you can actually write solutions to these discrete time systems in terms of the state transition map with a formula that's really extremely similar to the continuous time case. All right, so I'll just outline how you do this very quickly. I would suggest you kind of try filling in the details of this on your own. All right, so definition, discrete time state transition matrix. All right, so what we'll say is instead of a what's the verb? Instead of a continuous time, piecewise continuous function, we're now interested in sequences, right? So what I'll say is consider a sequence of matrices, A, which goes from Z into Rn by n. Oops. The discrete time state transition matrix with respect to A is a map phi, which goes from a domain D, which I'll just underline, into Rn by n, where D is defined as the set of pairs of integers k, k naught, and z cross z, such that k is greater than or equal to k naught. It's defined such that phi k naught is the solution to the discrete time recurrence x at time k plus 1 equals a of k times x of k, and x at time k naught equals the identity. Okay, so I have a couple of quick remarks to make about this. One of them is that as opposed to the continuous time case, we actually have to specify a separate domain for the discrete time case. All right, here it's really essential that we require k to be greater than or equal to k naught, unless we have some sort of condition where each matrix in our sequence is invertible. All right, so if we allow for k less than k naught, then we run the risk of solutions being actually non-unique, right? Because if the matrix is not invertible, there could be some ambiguity as to where we were before time k equal k naught. Okay? All right. So right here, this is just a discrete time recurrence that really directly translates the continuous time definition of the state transition matrix into discrete time. Okay. Fantastic. All right. So what you could then do is, after a little work, what you'll find is that you can write down the solutions, phi at k1, k naught, x naught, u, in the form phi of k1, comma k naught, x naught, plus the sum from j equals k naught up until k1 minus 1, phi at k1, j plus 1, b at j, u at j. All right? So you get, oops, make that nicer. You get a formula that's really analogous to the continuous time case, right? We have this term that doesn't involve any inputs, and we have this term that doesn't involve any references to the initial condition. All right? A consequence of this is that you can go ahead and compute your IO map rho by plugging into the output equation, and what you'll find is that you again get linearity in sigma cross u. All right? So the result of this is that discrete time, linear time varying representations yield formal linear dynamical systems. Okay, fantastic. We'll leave the lecture there. Thanks.